Hello and welcome to our Senior Design Day video through the University of Arizona. We are the Lightweight Catwalk team number 19047, sponsored by Caterpillar. The Lightweight Catwalk team consists of 6 engineers, Carter Kahn, Tanner O'Coin, Che Lane Neubauer, and Keisha Everett, who are the 4 mechanical engineers, and Saud Alkoff and William Serjana, who are the 2 industrial engineers. I'm Carter Kahn and I'll start this video and Keisha Everett will finish it. Starting with an introduction to the 797F haul truck made by Caterpillar, which the senior design team worked on. Some fun facts are it's 22 feet tall, it weighs over 1 million pounds, it has 4,000 horsepower, it has a 2,000 gallon fuel tank, and has a top speed of 42 miles per hour. And the catwalk is the area that lets the driver enter and exit the cab safely, and this is what the design team was set out to lightweight. Now starting with the problem description. As you can see in the picture, the arrow pointing toward the catwalk shows where the operator will be walking when getting in or out of the cab. Caterpillar tasked the design team to lightweight this catwalk by 2 to 5% from its original model. When haul trucks lose weight in their design, it directly translates to being able to haul a larger load. This is great for the user and an awesome selling point for Caterpillar. Caterpillar wanted us to design a lightweight model that could be used in other places of the truck to reduce the overall weight by a large amount. Some of the main requirements given to us by Caterpillar were, of course, being lighter than the previous model by 2 to 5%, maintaining all current attachments to the haul truck so that the old catwalk could be taken off and easily replaced with the new model, keep all handrail, mirror, and other mounts that are currently attached to the catwalk, maintain structural integrity in case of a fire, and meet or exceed 1 million loading cycles. We also had ISO standards we had to meet. ISO stands for International Standards Organization. These requirements included safety and no permanent deformation under certain forces of point and distributed loads.
To develop a structure that was both durable and lightweight, we chose to use an iterative approach called biomimicry modeling. In biomimicry, the design team looks for inspiration in biological models. The design spiral on the left shows the steps taken. We first asked, what do we want this structure to do? And the main answer to that question is to hold a weight on a horizontal surface. One of the natural systems that does this very well is the human body. In the body, weight isn't supported by simply propping up on top of a bone. Instead, muscles contract to pull closer to the trunk of the body and redistribute stresses. To abstract this method, instead of saying muscles contract, we say that weight is supported by using a tension to pull compression members toward the trunk of the structure. This is how we established our overall design. You may notice that the final step in the spiral is to evaluate, and that shows the iterative nature of this process. Other models that we considered were megafauna, beetles, and trees, but each of these failed in the initial evaluation phase. Once the first pass through the spiral is complete, the next pass starts. We also asked, how do we connect tension and compression members, and how do we reduce fatigue in high-stress areas? This illustrates how valuable this process was for us from beginning to end of this project. Here are some of the methods we came up with to emulate the human body. The key point of this design is floating compression or tensegrity, where compression members are surrounded by a sea of tension. In the final design, we used cylindrical struts to mimic bones, cables to mimic sinews and muscles, and stiffeners which were shaped and positioned similar to a rib cage. We also chose to make most of our joints rotating and use elastic dampening in the form of rubber padding. Here we have a side-by-side comparison of the new and original models. In the original model, you can see that a lot of bulk was used in boxy supports to the frame. The original stiffeners were very long and therefore had to be tall to prevent deflection. The profile of the original model has mostly square supports with several high-mass cantilevers. In the redesigned model, we've maintained the same key dimensions but added an inspection grate to the front section. We also divided the right-hand side into 3 sections and used the frames of those to add support and rigidity, basically using the frames as additional stiffeners. In the redesign, we connected the largest diameter struts to the outside frame walls at an upwards angle. This eliminates most of the cantilevers and produces a profile that looks more like a truss. The final difference is the use of stiffeners. By using curved stiffeners positioned on the short axis, or positioned hamburger ways if you remember elementary school, we were able to use less mass to achieve the same support. Some of the key design features are the net of tension, which is created by the cables. This reduces stress and redistributes that stress to help increase the machine life. Also, we've added separated attachment points, which makes the entire structure more scalable and more modular, and adjustable connection points, which help with ease of maintenance and assembly. The analysis of this project was also iterative. To fine-tune the design, we started with single sections and the simplest possible modeling. We then used these results to position all the detailed components, such as bolts, cables, and stiffeners. The final phase was to use true geometry, true materials, and forces with cables in place so we could see the effect of the tension network. Our redesign is 5% lighter than the original. Since some parts were off the shelf and SOLIDWORKS modeling wasn't exact, we also added an error margin of plus or minus 0.2% to account for those changes. Under a large distributed load, the maximum stress is on the thimbles which connect the cables to the frames. The thimbles are made of a higher strength material, so all stresses are below fatigue limits. The maximum deformation is around 2 millimeters on the front section decking. Under a standing load through a disc, the maximum stress occurs on stiffeners and is still well below the fatigue limit for that material. The maximum deformation occurs in the same area and is negligible. So this table shows that we met or exceeded each of the key requirements and verified them through different analysis methods. We inspected the SOLIDWORKS model to ensure closed gap construction and limit the size of debris that can pass through the surface. We also used measuring tools to ensure that attachment points align and also that they sit flush with one another and don't have misaligned angles. We compared the original and redesigned volumes in cubic centimeters to ensure accuracy and fine error margins. And we demonstrated that stresses are below fatigue limits, so components are unlikely to fail due to cyclic loading. Finally, in addition to the original requirements, the sponsor asked that we limit surface deflection to 3 millimeters, which we have also demonstrated success in. Of course, social distancing orders have impacted the project in certain ways. We weren't able to complete the physical components testing or determine the natural frequency of the structure. Luckily, though, the majority of our verification could be done with software on home computers, and additional confidence testing is prepared for when normal operations resume. Overall, we're both confident and proud of this redesign and any future lightweighting projects it may influence. That's it from us, and thank you for watching. And thank you to Caterpillar, Pat Caldwell, and the University of Arizona for your time, support, and stern encouragement.